Sem 6 Unit 2 Quantum Chemistry. I am Dr. Devang R. Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Well, these are the syllabus points that we are going to discuss. Not all, few of this up to operator. Quantum Chemistry, Unit 2, 14 marks weightage. We'll start with setting up of operator of different observables, Hermitian operator and theorem related Hermitian operator. That important theorems concerning Hermitian operator we are going to discuss in this lecture. Then in next lecture we're going to discuss regarding particle confined into a three-dimension box, and we're going to derive energy for the particle confined in this three-dimension box and learn the degeneracy of that electron confined into three-dimension box. Then after we're going to discuss regarding rigid rotator and rotational spectra, and then the Schrodinger equation in which the spherical polar coordinates for hydrogen atom, that is application of Schrodinger equation on hydrogen atom, we're going to study, and from that equation we're going to separate variables, and after getting the separation of the variables we're going to discuss the solution of r, theta and phi equations. So this is the complete syllabus for quantum chemistry unit 2 for CH6502. Reference book, two books I will going to recommend. One is Quantum Chemistry by A.K. Chandra, and the other one is Quantum Chemistry by R.K. Prasad. And if you want to study foreign author, you can go for Quantum Chemistry by Levin. Now, why to study quantum chemistry? Because I already said to my students that without temptation there is no work, and without work we can't get any knowledge. So a temptation is required for motivation, so that we can take little interest in the subject, and that way we can study that subject in a proper way. So I will begin with application of quantum, where quantum used. First, to describe the atomic structure, how the different physical phenomena or derivatives, or we can say physical observables associated with particle, and what is the behavior of electron. We can describe every sort of information from position to momentum to total energy of electron confined into an atom. So to describe atomic structure we need to study quantum. And when you have idea regarding the electron behavior within the atom, then with the help of that you can study how the atom going to convert into a compound. And in this compound or atom, when you provide energy and electron excitation take place, you study the spectra. So in spectrum chemistry, or to study the spectra, you can use quantum. Next, whether there is a covalent bonding between two atoms in the molecule. If you want to study that one, you need to use quantum. And in certain chemical reaction, whether it is organic or inorganic, to study the chemical reaction and its mechanism, quantum is essential. Quantum gives a behavior study of the electron, and electron have spin rotation, orbital rotation, and these two rotation give rise to magnetism. So to study the magnetic property of the compound, we need to study quantum. And quantum gives us information regarding the different orientation of atom in space, the lone pair repulsion, lone pair bond pair repulsion, every kind of stereo arrangement required to study the behavior of electron, and for that quantum is essential. To study the semiconductance of the compound, we use quantum. So these are certain areas where we study quantum. Let's begin with the interpretation of psi, psi square and psi star. Psi is a wave function and it can be compared with the amplitude of the wave. Wave function has no physical interpretation. If the solution of wave function is psi x, if we are thinking that the particle is moving on x direction only, then the solution of that wave function is denoted as psi x. Then the electron in the boundary of, let me show you, electron in the boundary of x plus dx. This x is the x direction and dx is the displacement of particle on x direction. That is a minimum distance covered by the particle on x direction, and its value is indicated as psi square dx. Means in a volume of dx, in a volume of space of dx in x component, x direction, the probability of finding electron is indicated by psi square. The wave function should accept the following conditions, which already you have studied in lower standard, that at one point the value of psi must be single, must be 1. The value of psi must be finite. It shouldn't be infinite. It must be finite at one particular position. The value of psi for all x's must be continuous. It must be continuously changed. And the value of psi must be normalized. Normalized means integration psi star dx or d tau should be 100%. That is explained as 1. If the wave function follow all those 4 conditions, then that wave function is considered as normalized wave function. So the condition of normalization is explained by Max Born, that psi square indicates the probability density. That means instead of exact position in space, you can define the position of particle through probability density. Say for example, I always give this example to my first year student, that if you at any point at nearly 10 to 12 o'clock, if somebody will ask you where is your mom, you will show your address and you say that she might be in the kitchen, because that is the time for cooking food. So the most probability of being your mom in the kitchen, that indicate the probability density, but it is not necessarily right position, because she might be somewhere outside in the drawing room, in the bedroom, or maybe outside the house to get some miscellaneous things. But most probably at those period of time she is cooking and she might be in the kitchen. So somebody will ask you, then without keeping any eye on your mother's position, you say she might be in the kitchen. So that indicates the probability. So here Max Born says that instead of indicating the exact position of electron, you need to show the probability density. And that probability density can be indicated by integration minus infinite to plus infinite psi star d tau is equal to 1, where d tau is the volume of space on x, y and z direction in the Cartesian coordinates. If this value isn't 1, then by multiplying n square you get that 1, then that n is known as the normalization constant. So or if the wave function is not normalized, then by multiplying with the normalization constant you can change that wave function into a normalized, well-behaved wave function. Now next condition is the orthogonal and orthonormal wave function. If we have two different wave function, then condition of orthogonality for those wave function can be explained mathematically like this: integration minus infinite to plus infinite psi a into psi b. This is the wave function associated with arbitrary a, and this is the wave function associated with arbitrary b. So two wave functions are there, and their integration in data volume, if turns 0 where a is not equal to b, then these wave functions are orthogonal to each other. They are not normalized. Now we need to go for the orthogonal wave function, and orthogonal wave functions are free from each other. Orthonormal set, that means both the condition together. These are both the condition together. If we have two different wave function, then integration minus infinite to plus infinite psi a into psi b d tau is equal to 0 where a is not equal to b, and integration minus infinite to plus infinite psi a dot psi b d tau is equal to 1 where a is equal to b. If both this condition apply together, then it is orthonormal set. Now let's see the example or proof of normalization. If we have any wave function, and if we will take the integration of the square of that wave function, then it must be 1. Then we can say that it is a normalized, well-behaved wave. So this is the question. Wave function psi n is equal to n into sine n pi by ax. Then calculate the value of normalization constant, that is this n, where the value of x is between the limit of 0 to a, means 0 is less than x is less than a. That means the position x in x direction, where the limit dx would be between 0 to a. That means particle on x direction moving 0 to a. That means source to point a, and there the wave function value would be n sine n pi by ax, and we need to find out the value of n. Let's see the solution. Integration psi n into psi n. Psi square means psi n into psi n d tau is equal to, now there is the limit condition. It should be integration 0 to a. First time psi n, that is n sine n pi by a into x, into second time psi n. So same value we need to put here, n into sine n pi by ax. Now n into n, that is n square, and it is a constant, so we should keep this constant outside the integration. So we have kept this n square outside the integration. Integration 0 to a. Now sine into sine, that is sine square n pi by ax. Now using this trigonometry relation, that sine square is equal to 1 by 2 into bracket 1 minus cos 2 phi, where phi we can take as n pi by a into x. So instead of sine square n pi by a into x, if we're going to put this value, we can write 1 by 2 1 minus cos 2 into n pi by a into x. So that value we can substitute for this sine square in this equation. Here cos 2 phi is equal to cos square phi minus sine square phi is equal to 1 minus sine square phi minus sine square phi is equal to 1 minus 2 sine square phi. So 2 sine square phi is equal to 1 minus cos 2 phi. This relation is how this relation is going to be obtained. Now sine square is equal to 1 by 2 1 minus cos 2 phi. So sine square phi is equal to 1 by 2 into bracket 1 minus cos 2 phi. Now here we're going to take phi as n pi by ax, and if we'll take that one, we're going to get here integration psi n squared d tau. This one, psi n squared d tau is equal to n square, that is n square integration 0 to a 0 to a. Now instead of sine square n pi by ax, we need to write 1 by 2 into bracket 1 minus cos 2n pi by ax dx is equal to 1. So that is equal to n square by 2. This 2 is also constant, so we kept it outside the integration. N square by 2 and 1 minus cos 2 pi by a x and its dx integration value 1 minus 0, because there is one limit 0 to a. So that 0 value is taken, so it's 0, dx is equal to 1. Therefore, n square by 2, now this 1 minus 0 is equal to 0 dx, that is dx is equal to 1. So that value is equal to n square by 2a is equal to 1. So n square is equal to 2 by a, and therefore we can write n is equal to under root 2 by a. So our answer, normalization constant for this equation, n is equal to under root 2 by a. So if we are going to put this value over here, under root 2 by a, and that value when we put here, then our condition of normalization is proved. So this is the example as well as the proof of normalization. Now practice this problem yourself. In the wave function psi is equal to n into exponential minus im phi, calculate the value of normalization constant n, where m is the constant and 0 less than or is equal to phi less than or is equal to 2 pi. When you do that calculation as I have shown you earlier, you will get the answer or the solution, n is equal to under root 1 by 2 pi. So this is the problem for self-study. If you have any doubt, you may ask me in the email. Next, that is eigenfunction and eigenvalue. Already you have studied in your semester 4 about this eigenfunction and eigenvalue. The same thing I am going to explain you here. If you have a function and you are going to use an operator on a function, and that operation, when you operate on this operand, that is the function, it change into another function, but that function is the same one. So when operator operate on a function and it gives the same function with a constant value, then that function is called eigenfunction and the constant value is called eigenvalue. Here we have the example. I have sin x, sin hx, sin ix. These are the functions of operator d square by dx square. So function 1, 2, 3, etc. And we have one operator, that is double differentiation operator, d square by dx square. Now let's take the example. If we have a function e exponential, that is exponential minus ix, is the function of operator d by dx, then d by dx into e exponential minus ix, and that minus is represented minus a into e exponential ix. This is our wave function. So instead of this I can put psi. So d by dx psi is equal to minus a psi. That minus a would be the constant value and psi is the same function which we have taken before the operation. So same function is going to be obtained after the operation done by the operator on operand. We're going to get the same function with the constant value. That same function is known as eigenfunction and the constant value is known as eigenvalue. Here minus a is the eigenvalue of operator d by dx, and exponential minus ix is the eigenfunction of operator d by dx. Similarly, indicate that sine 2x is not the eigenfunction of d by dx operator, but it is the eigenfunction of the double differentiation d square by dx square. This is the question. Let's get the solution. Some more example where functions are an eigenfunctions. This is you need to practice yourself, and these are the example. Operator d square by dx square, you have sin x, we're going to get d square by dx square, sin x is equal to minus 1 sin x. So function, now after the operation we'll get that function back. It means that d square by dx square operate on sin x, gives the sin x with minus 1. So this wave function is called eigenfunction, and minus 1 is going to be the constant value, that is eigenvalue. D square by dx square on sin hx, when we are going to operate double differentiation on this wave function, we're going to get minus h square sin hx. So same function is going to be obtained. That means this function is also known as eigenfunction, and this minus h square is eigenvalue. Similarly, d square by dx square on sin x ix, then it will going to give us minus 1 sin ix. The same function is obtained. So this is your eigenfunction, this is your eigenvalue. Similarly, d by dx operate on exponential x, we're going to get plus 1 exponential x. So same function is obtained. After the operator operate on ex, we're going to get the same function, which is eigenfunction, and this is eigenvalue. So this is more example of eigenfunction and eigenvalue. For sin x eigenfunction, we have eigenvalue minus 1, here minus s square, here minus 1, and here plus 1. These are the eigenfunction. And this sin x, sin hx, sin ix, and exponential x, they are eigenfunctions. Now some more example where the functions are not an eigenfunctions. So here you can see that operators is a single differentiation d by dx, and we have function 4x square, cos x, and log x. Now 4x square converted into 8x, so the function get changed. So there is no eigenfunction eigenvalue relation over here. Cos x converted into sin x, here also function get changed. So there is no eigenfunction eigenvalue kind of relation over here. And here also log x converted into 1 by x, it means there is no eigenfunction eigenvalue kind of relation found here as well. Now concept of operators, which already have studied in semester 4. Operators, an operator is a symbol, is a mathematical symbol for a certain mathematical procedures which transforms one function into another. That means operator operate on function and change that function to another function. Here you can see that operator operate on any function. This dot doesn't mean multiplication every time. It means operator operate on function and change that function to another function. Here we have operator d by dx and the function that is sin x, and that function which get operated is known as operand. So this function is known as operand. An operator operate on operand and change into another function. The function on which the operation is carried out is called operand. This is operand. Generally, an operator is written with this symbol hat overhead. So here you can show it or indicate it overhead symbol. Now characteristic of Hermitian operator, the turn over rule. Quantum mechanical operator obey following condition is called Hermitian operator, and the condition is if operator A has two eigenfunctions psi and phi, then integration psi a phi d tau is equal to integration phi a psi d tau. If this two is similar, then this operator A is known as Hermitian operator. Means one time you can see here in the bracket operator operate on function phi and then multiply with function psi d tau and its integration. Now another time operator A operate on psi and then multiply with phi and its integration. If these two integration comes similar, then it is called Hermitian operator, and it is also known as turnover rule. One after the other, the operator operate on different function and their integration in the volume of d tau if similar, then that operator known as Hermitian operator, where psi and phi are real functions and operator A is a Hermitian operator. The other way you can indicate in this way, integration psi star, that is the complex conjugate of this wave function psi, operator A operate on phi d tau is equal to integration phi operator A operate on psi whole complex conjugate d tau. That is also similar. So these both conditions are known as Hermitian operator condition, where psi is the complex and psi star complex conjugate and d tau is a volume in space in x, y and z Cartesian coordinates direction. Operator A here known as Hermitian operator. Let's prove that d square by dx square, that is double differentiation symbol of double differentiation, is a Hermitian operator. Suppose we have function psi exponential ix and function phi as sin x. These are the accepted wave functions. So for that left hand side, that is this two part, let's say in the previous case, this is called left hand side and this part is called right hand side. Similarly, this part is called left hand side and this part is called right hand side. So that we are going to indicate over here in the proof of this. Yes, proof that d square by dx square is a Hermitian operator. There we are going to use left hand side and right hand side. So for that, left hand side is equal to integration psi star. So we are going to take the complex conjugate of this exponential ix. Uska complex conjugate we are going to use here. A operator operate on phi d tau is equal to, now instead of psi we need to put its complex conjugate, so exponential plus ix, now in complex conjugate turns minus ix. So instead of exponential plus ix we should use exponential minus ix, because this is the complex conjugate of this wave function psi. So the plus get changed to minus. D square by dx square for this operator, d square by dx square, instead of a we can put d square by dx square. Sin x over here dx, instead of d tau we are using dx because only x component is there, so instead of d tau we can use dx. So this is our left hand side. So let's get that value. Integration exponential minus ix, this one, and when we apply this operator on sin x, d square by dx square on sin x, then we can get minus 1 sin x, because it has eigenfunction eigenvalue kind of relation. So when operator d square by dx square operate on sin x, we're going to get the same function sin x with constant value minus 1 dx. Now minus 1 is a constant value, we can keep outside the integration. So that gives in red color -1 integration exponential minus ix into sin x dx. So this is our left hand side. Now let's take right hand side. Now in right hand side, this phi will come out of the operation and psi star will goes inside for the operation. So right hand side integration phi operator a psi complex conjugate d tau. Let's put the value psi, that is sin x. So here we need to put sin x. Now operator a, that is d square by dx square, so we put d square by dx square, and psi, that is this complex conjugate, that's why minus x. This you do not need to put if you put minus, and if you put this one you need to write plus here. This is a typological mistake. So bracket only but no star, exponential minus ix d tau. So integration sin x remain as it is, and d square by dx square exponential minus ix can be written as minus I square exponential minus ix sin x dx. Now I square, i's value, that is imaginary number, under root -1. So under root -1 whole square, that is represented as -1. So if we're going to put the value of I over here, we're going to get -1. That is a constant value. We need to keep outside the integration. -1 integration exponential minus ix into sin x dx. And now compare this left hand side with the right hand side. Both is similar. So left hand side is equal to right hand side. Therefore, we can prove that the operator is a Hermitian operator because it gives turnover rule. Left hand side is equal to right hand side, that is turnover rule, and therefore we can prove that this operator is a Hermitian operator. Now let's study the theorem 1 associated with this operation, Hermitian operator. So the statement for theorem 1 is we need to prove eigenvalue of Hermitian operator are always real. Now explanation. Suppose operator A is a Hermitian operator and psi is an eigenfunction and A is an eigenvalue, then A psi is equal to A psi. This is eigenfunction eigenvalue kind of relation, as we know that when operator operate on a function gives the same function with the constant value, then that function is known as eigenfunction and the constant is known as eigenvalue. So this one relation we have obtained. And A psi whole complex conjugate is equal to A star psi star. When you remove the bracket, you get operation done on psi. You'll get A psi and its complex conjugate. So A star psi star. This is equation number 2. By multiplying equation 1, this one, with psi star and taking integration, we get integration psi star, then we need to multiply with this one. A psi d tau is equal to integration psi star A psi d tau is equal to A, because when operator operate on psi gives A psi, so that A psi we have placed. Now A is a constant value. We need to kept it outside the integration. So we'll get A integration psi star psi d tau. This is our left hand side. Now integration psi star A psi d tau is equal to A psi star d tau. That is equation number 3. By multiplying equation number 2 with psi, taking integration. Now we need to multiply this with psi and we need to take the integration of it. So integration psi into A psi whole star d tau is equal to, now we need to put the value from equation 2, this one, psi A star psi star d tau is equal to, now A star is a constant value, we need to keep outside the integration, So A star integration psi star d tau. That is equation number 4. But here we have one condition. For to prove this, we have one condition, that is operator is a Hermitian operator. So our operator A is a Hermitian operator. It gives turnover rule. So integration psi star A psi d tau is equal to integration psi A psi whole star d tau. That is the condition of the Hermitian operator. So we need to compare equation 3 with equation 4. Here, according to equation 5, left hand side of equation 3 and left hand side of equation 4 are equal. So their RHS are also equal. So A integration psi star d tau is equal to A star integration psi star d tau. That means this part of equation 3, that is right hand side, is equal to right hand side of equation 4, and these are those two right hand side. And this is only possible if A is equal to A star, means A should constant. It should not get changed after making its complex conjugate. Means A is equal to A star, means it is a real value. So we can prove that the eigenvalue of Hermitian operator are always real. Now second theorem, that is eigenfunction of different eigenvalue for Hermitian operator are orthogonal, or we need to prove that integration psi star d tau is equal to 0. Means eigenfunctions of different eigenvalues for Hermitian operator are orthogonal. Two functions, we need to prove that they are orthogonal to each other. Let's see the explanation. Suppose we have function psi1 and psi2. As I already said, that to prove orthogonality, you need to take two different functions. For a single function, only normalization condition can be established. For orthogonality, we require minimum two or more than two functions. So here, let's start with assuming two different functions, psi1 and psi2. They are eigenfunction of operator A, and their respective eigenvalues are A1 and A2. That means when operator A operate on function psi1, it gives A1 psi1, and when operator A operate on psi2, it gives A2 psi2. So according to condition of orthogonality, integration psi1 psi2 d tau must be 0, or integration psi1 psi2 star d tau must be 0. Or according to eigenvalue equation, we can write A psi1 is equal to A1 psi1. Already I have said that operator A operate on psi1 gives A1 psi1. This is eigenvalue kind of operation. And operator A operate on psi2 gives A2 psi2. So this is equation 1, this is equation 2. Now multiplying equation 1, this one, with psi2 star and taking its integration, we're going to get integration psi2 star operator operate on psi1 d tau is equal to, now when operator operate on psi1, we can put the value A1 psi1. So substituting that value of this A psi1 as A1 psi1, we'll get integration psi2 star A1 psi1 d tau is equal to A1, because it's a constant, we need to keep it outside the integration. So integration psi2 star psi1 d tau is equal to A1 integration psi1 psi2 star d tau. That is equation number 3. But A is the Hermitian operator. Hermitian operator, that means operate on functions psi1 and psi2 individually, then multiplying with psi1 and psi2 one after the other, and their integration must be similar. That is turnover rule. So integration psi2 star a psi 1 d tau is equal to integration psi 1 a psi 2 star d tau is equal to, now a psi 2 star d tau, that means this value we can put it here. We get s2 star because that is the eigenvalue and it is constant, so kept outside the integration. A2 star integration psi 1 psi 2 star d tau. So A2 integration psi 1 psi 2 star d tau. Therefore, A2 is equal to A2 star. That already we have proved in the earlier theorem. According to equation 3 and 4, this and this equation 4, A1 integration psi 1 psi 2 star d tau is equal to A2 integration psi 1 psi 2 star d tau. Therefore, A1 minus A2, when we kept this side, A1 minus A2, and this 2 is common, integration psi 1 psi 2 star d tau is equal to 0. Now, A1 is not equal to A2, then this one is not equal to 0, and A1 is equal to A2, this one is equal to 0. It means integration psi star d tau, psi 1 psi 2 star d tau is equal to 0. So it is proved that both the eigenfunctions are orthogonal to each other. This is our theorem number 2. Next theorem is about the commutator. Commutator are the two operators when operate with one after the other. Operator A operate on B and operator B operate on A, and A into B minus B into A is equal to 0, then both the operator commute with each other. If operator A and B commute each other, then their eigenfunctions are also equal. Prove it. So we need to prove that if these two operators commute with each other, their eigenfunction must be equal. This is the solution. Suppose function of operator A is psi I. So A psi I is equal to AI psi I because eigenvalue relation, where AI is the eigenvalue. Here operator A and B commute each other. So AB psi I is equal to BA psi I, one after the other. This value is called commutation relation, is equal to B. A operator operate on psi I is equal to B. Now A psi I is equal to AI psi I. So that we can put it over here. Now second, that is A B psi I. So A B psi I, this side. A B psi I means B operate on psi I, but A written as AI B psi I. This indicates that B psi I is the eigenfunction of operator A, which has eigenvalue AI. Now next, that is theorem number 3. 3 is for commutation and this is fourth. If one group of orthogonal function psi I exists, which are the eigenfunction of operator A and operator B, then this operator commute each other. The reverse statement than the previous theorem. This is theorem number 4. Solution of theorem 4. Suppose one of the function chosen from psi I is equal to phi, where phi is equal to sigma I ci psi I. So it's a set of orthogonal functions psi I, group of orthogonal functions psi I. Operating this function with operator A commute with B. A B is equal to AB minus BA phi, where phi is a set of group of operator sigma I ci psi I is equal to BA minus AB and we will going to substitute the value of phi over here, sigma I Ci psi I. So A operator B, AB, sigma I Ci psi I minus BA sigma I Ci psi I. Now sigma I psi Ci, that is a constant value. Operator A kept outside and operator B first operate on psi I. So minus sigma I Ci. Now B kept outside and operator A operate on psi I. That is our equation number 1. A psi I is equal to Ai psi I and B psi I is equal to Bi psi I. That is the eigenvalue condition. Substituting this value in this equation, we are going to get AB minus BA phi is equal to sigma I Ci A. Now instead of B operate on psi I, we are going to put Bi psi I minus sigma I Ci B. Now instead of A psi I, we need to substitute Ai psi I. So we have substituted Ai psi I over here. So now similar value kept outside, that is sigma I Ci Bi will going to get, when we keep Bi outside, now the operator A will operate on psi I, and when we kept Ai outside, now operator B operate on psi I over here. So sigma I Ci Bi Ai psi I. Now instead of this Ai Ci, we can put value Ai psi I. So we have put that value Ai psi, and instead of B psi I, we need to put Bi psi I. So we have put Bi psi I, and both is similar, so it gives value 0. It means that both the operator operate with or commute with each other. Here phi is the selected function which should not be 0, so it is proved that AB minus BA is equal to 0, because function should not be 0 and therefore operator's value must be 0, and that prove that if group of orthogonal of functions psi I exist, which are the eigenfunctions of the operator A and B, then operator A and B must commute with each other. That is proved. Now this is fifth and final theorem, that is for your practice. I am going to put it here. Yeah, this one. If two Hermitian operator A and B operate, B commute with operator A. So A and B are Hermitian operator and they commute with each other. We need to prove psi 1 and psi 2 both the eigenfunction of B and A1 and A2 are the eigenvalues. Then prove that integration psi 1 star B psi 2 d tau is equal to 0. Means both the function in respect with operator B is orthogonal with each other. That we need to prove in this theorem. This is the solution. We have A psi 1 is equal to A1 psi 1 and A psi 2 is equal to A2 psi 2. So operator operate on psi 1 gives the psi 1 wave function with constant value A1, and when operator operate on psi 2 gives psi 2 with constant A2. That means this is the eigenfunction eigenvalue kind of relation. Now thinking about this integration, we're going to get integration psi 1 star B A psi 2 d tau is equal to integration psi 1 star B A2 psi 2 d tau. So instead of A psi 2, we can put A2 psi 2. So that value is substituted over here. A2 is the constant, so we need to keep it outside the integration, and we'll get integration psi 1 star B psi 2 d tau. That is equation number 1. Here A and B commute with each other, so we need to apply the commutation condition of A and B, and therefore integration psi 1 star b a psi 2 d tau is equal to integration psi 1 star a kept outside, b kept inside, Hermitian operation b psi 2 d tau is equal to integration b psi 2 a star psi 1 star d tau. A star psi 1 star is equal to a1 psi 1 star, that we can substitute the value over here. So a1, which kept outside the integration, gives b psi 2 psi 1 star d tau is equal to a1 psi 1 star b psi 2 d tau. That is equation number 2. On comparing right hand side of equation 1 with equation 2, we get the Hermitian kind of relation. A2 psi 1 b psi 2 d tau is equal to a1 psi 1 star b psi 2 d tau, or a2 minus a1, when we will kept this to this side, we'll get a2 minus a1 integration psi 1 star b psi 2 d tau is equal to 0. If a2 is not equal to a1, then integration psi 1 star b psi 2 d tau is 0. But if a2 is equal to a1, then this is not 0. So we can say for the following, let me say the statement. Well, I am talking about this. If two Hermitian operator A and B and operator B commute with A, and psi 1 psi 2 are both eigenfunction of B, giving A1 and A2 are the eigenvalues, we need to prove psi 1 star B psi 2 d tau is equal to 0. This is only possible if A is not equal to B. That solution we have discussed over here, and we get that relation over here. A is not equal to B, then and then only A is not equal to B, then and then only this condition psi 1 and psi 2 are orthogonal to each other through operator B, that can be proved over here. So when you study quantum, you feel life sucks, it sinks, and you feel that you are hating yourself. But hey, don't be so negative, because when you try to take interest, you can learn quantum chemistry, and it is the basic chemistry on which you can learn so many applicable sciences. This is enough from my end. Thank you for paying attention to this video lecture. Keep asking questions, as you know asking question is a beautiful way to gain knowledge. Thank you.